Hello everyone, in this video we're going to look at chapter 9, one or two sample estimation problems. The first one is what's the meaning of sample estimation? It means if we want to estimate the if we have like 1 million bottle of something, or maybe Coca-Cola, we want to find the mean value or the standard deviation of the weight of the 1 million bottle. It's too many. We cannot measure one by one. Even you have a machine, you still have to do a lot of things, right? So sometimes we have the population is too big. It's impossible for us to measure one by one. So then we're going to use the sample mean or sample standard deviation to estimate the population mean and the population standard deviation. Okay, that's what we want to do in chapter 9. All right. So we're going to use the okay. First, let's look at section 9.2. Then this is pretty. You can read it like just by yourself. Statistic interference may be divided in two major areas. First one is estimation, which we're going to do in this chapter is estimation. Okay. And second one is test of a hypothesis. Hypothesis we're going to do next. I think it's next chapters. Okay. So first is estimation, then hypothesis test. But the estimation, first we'll look at the point estimate. Point estimate of population. Okay. Point estimate of population parameter theta is a single theta of statistic of the population, big theta. For example, the value x bar of the big x bar, small x bar, and of the statistic of big x bar computed from a sample size. Okay, a point estimate of population mu. So for the point estimate of the population mu, first we have the estimate of the proportion. Okay, for example, proportion. Given a sample, the proportion is going to be x over n. X is the numbers, is the estimate of true number, okay, or the true true samplings. N is the total samplings. So divide is the proportion. Okay. For example, the n could be the total all the students. No, n is also a small sample. Okay. So n is a sample of math 240. Okay. But population is whole math students at UWC. But we just look at a small sample, math 240 students, and x will be represent the passing number of students who pass this class. Okay, the number of pass. Then the proportion is passing ratio. Okay, so x over n is estimate proportion. So from a sample. All right. So what are the desirable property of a good decision function that would influence us choose one estimate than the other one? So what do we want? We want this estimator to be unbiased estimator. Okay. So unbiased, which means we have the E, whatever you want to estimate, or E sigma will equal theta. So they have exactly the same expectation. If the population and the sampling, they have exactly the same. For example, mean value, they have exactly the same expectation on the mean value. This means that sampling estimator is unbiased estimate of the parameter. Okay. So statistics is a theta. Okay. This is whenever we talk about a statistic theta, this is from sampling. Okay. Whenever we talk about a theta, we say parameter is population. Okay, whenever you say parameter is population, it's a population. Okay, so it's for the population. because parameter is something which is what? It's kind of like a true thing. It's it's authentic, true. Okay, because it contains everything, so that's why we said parameter is population. Okay, you gather all information together, you find out one number, which is a parameter. This is for everything. Okay, parameter. Why? When you're first sampling, actually, we use that. It's kind of like a statistic. It's not a parameter. It's not for. It is. We can use that for estimate the parameter, but it's still from a small sampling. Okay, it's just how you call it. This is how you prove that the sampling S square is the best estimate for the parameter sigma square. So basically, you want to prove that AS square equals sigma square. If their expectations are exactly the same, equal the sigma square, then it is the best estimator. Okay, so use the variance to estimate the population variance, sampling variance and population variance. It makes sense, right? Alright, so if we consider all possible n pairs, the estimate of some parameter theta, the one with the smallest variance is called the most efficient estimate of theta. Okay, sometimes we may have the same, we may have some estimator, they all have the same, they all are unbiased, but the smallest variance is the most efficient estimator. Alright, I think you can read all of this talking about the interval estimate. Basically, it means, for example, if I say the mean value of the weight, I cannot say that. The mean value, now I want to estimate 1 million bottle, the weight of 1 million bottle of some drinks, okay, of Coke. You can see that, okay, of any drinks. All right. So as I said, it's very hard to measure 1 million bottle one by one. It takes a lot of time consuming, cost is too much. So basically, what we do, we want to estimate, for example, just 1,000. That's not that many, right? I want to estimate 1,000 bottles and find the mean value of the weight. So what do you have? You have a X bar. For example, it's just 1.05 pound. Okay. So 1,000 bottle, the average weight of 1,000 bottle is 1.05 pound per bottle. So what happened is, we want to use this 1,000, the average of the 1,000, the sampling average, to estimate the population average. Okay, so the population average the population mean value will not exact. Sometimes might be. It's very likely not exactly the same thing as the X bar. Okay, the average of 1 million bottle, it might be 1.06 or might be 1.051. So most likely, they are not exactly the same thing. So what do? We use a sampling mean value to make a interval. Okay, so we might make an interval plus something or minus something. Okay, we're basically going to make an interval. The interval, this E is represented the error. Okay, so it's kind of like, okay, now I know the average mean value of the 1,000 bottle is 1.05. Now I'm very confident the average mean value of the 1 million bottle is from 0.8 to 1.5 pound. So kind of like you make a interval, say I'm confident that population mean value will be any number in this interval. Okay, I'm 100% sure it's from 0 to 100 pounds. For sure, you don't have any bottle is 100 pounds, right? So that's the big interval you give, the more confident you will be for the estimation. Okay, so that's the meaning of the interval estimation. Okay, give a confidence interval. Give a confidence, for example, 95% confidence interval. Give a confidence, and you have to find out the confidence interval. So let's look at the single sample estimate the mean value. Single estimate the mean value. So you can please read this. It's just the sampling distribution again. What do we have previously? X minus mu over sigma over square root of n is a base normal distribution 0, 1. Okay. So what do we have for the sigma known? If sigma square is known, if sigma square is known, then the mean value will be x bar minus, as I said, e, and x plus e is the error. The e is based on your confidence. Okay, so what do we have for here? The e equals z alpha over 2 sigma over square root of n. Why is it like that? Why is e equal that? So if you look at the formula, x bar minus mu over sigma over square root of n equals z score, right? Then x minus mu, the difference between x bar minus mu equals z sigma over sigma z times sigma over square root of n, give you a alpha. So now this is the difference between the sample mean value and the population mean value. Sample mean and population mean, they have a difference. This is the difference. This is the error here. Why do I have alpha of 2? Because it's symmetric. Okay, left and right, it give you alpha of 2 confidence interval. Okay, you look at the that has an explanation of alpha of 2, because if you look at this, left side alpha of 2, right hand side alpha of 2, and the middle is 1 minus alpha. Okay. So there are example 9.2. It gives you the alpha. For example, the average zinc concentration recovered from a sample measurement taken in 36 different locations in the river is found to be 2.6 gram per millimeter. So x bar equals 2.6. Okay, that's the sampling, and n equals 36. 36 sampling give you mean value is 2.6. Find the 95% of, or 99%. You find each one by each. So first find 95% confidence interval for the mean zinc concentration in the population in the whole river. So it's going to be 2.6 minus something, 2.6 plus something. You have to give a 95% interval. So how do we find that? And because a formula is mu x bar minus z alpha of 2 times mu sigma over n. So basically, we just apply the previous given formula. So it's 2.6 minus 95%, alpha equals 95%. Then we have actually we have to look at the z alpha of 2, which is 1 minus 95% divided by 2. Okay, so this one give you 0.025. Okay, but we always want to add, it's going to be, okay, the middle point in the middle side is 95%. So here is 2.5%. Here is 2.5%. What do we have? We're going to estimate this point. This point is going to be z is going to be 0.975, which is 1.96. Okay. Alright, so you plug into here, so it's 1.96 times sigma is given 0.3, square root of n is given 36. Okay, then 2.6 plus 1.96 times 0.3 times square root of 36, and then you find the interval. Okay, the key part I think is find the z-score. Okay, the z-score of that So basically just plug it in. If you graph a picture, the middle is 95%, each side is 2.5%. You're looking for this side, this point is 0.9. You have to add those two together, right? Given this point, you have to add the left side. So it's going to be 975 equals 1.96. Once you graph the picture, it's very simple for you to find it. Next one is the same idea. You graph the picture, you find out this, the middle part is 99%, and you actually find 995. Okay, for the 99%, so this is 99%, and this is going to be 0.05. Right, so 0.5%, my bad. It's 0.5%. This side is also 0.5%. So we're looking for this point, this part. From left to until this point is 0.995. Okay, so we're looking for 0.995. What is z value? Give you 0.995. Basically, you're looking for something z less than something. What number here? Give you 0.995. And then this value is 2.575. Okay, you can use your z-score table. All right, this is how you find out the confidence interval for population mean. Okay, please read the theorem 9.2, because we have that E equals, if you look at the E is the error. Sigma over, z alpha over 2 sigma over square root of n. Now I solve for n, I square both sides. You got E square equals z alpha over 2 square times sigma square over n. So I can multiply both sides by n, so it's ne square equals z alpha over 2 square times sigma square. And then you got n equals z sigma, okay, and over n square square. So basically, that's why you have not n, e. That's why you have the n equals z alpha over 2 times sigma over e square. The e is the error, is the estimated error. Okay, so that's why you have this formula for 9.2. All right, so sometimes it might give you a error. You ask you to find out what sample size you need. All right, in the video of the homework, I will show you how to use a StatCrunch. StatCrunch to do the to do all of this estimation work. Next is one-sided up, one-sided bound, a lower one-sided bound. Okay, basically you just have, previously is two sides, right? X minus z alpha over 2, because left the alpha over 2 and sigma over square root of n, x bar plus z alpha of 2 and sigma of square root of n. So previously you have lower bound, this is you have two-sided. Now you just have one-sided, so you just have x bar, and until this lower is here, it's still alpha, so we just have plus z alpha. Okay, because don't divide by 2 anymore, just one side. One side must give you z alpha confidence interval. Alright, so for that's for case of sigma is known. Now we look at if sigma is unknown. When sigma is unknown, we know the distribution is changed into t distribution. So we're going to use the t distribution of x bar minus mu over s over square root of n. Previously we have sigma over square root of n. So z equals x minus mu over sigma over square root of n. The only difference is sigma is known, use z distribution. Sigma is unknown, is t distribution. Everything else exactly the same thing. Okay, so you have the estimation interval is x bar minus t alpha over 2 sigma over, not sigma anymore, we don't have sigma, s over square root of n, x bar plus t alpha over 2 s over square root of n. So you are going to have the same interval, but just change the sigma into s and z alpha of 2 into t alpha of 2. Both of these numbers will be given, we have to find from the table, t distribution table or z score table. Alright, So you can please look at an example 9.5 yourself. You should be able to look at the example. Basically, x bar is given, s is given, n is given, x bar is given, s is given, n is given. The only thing you need to find is t value. Please find out the t value, see if you understand it. So if you are looking about 95%, you are looking at t 0.025, okay, 0.05, because you have two sides. Each side is 2.5%. You are looking for this value. Say if you can find the value from the t distribution table. Once you find the t distribution table, the t value, you just plug it in, you get a number. Okay, so let me see, what do we stop here? Alright, so let me see. Alright, so in this in next chapter about 9.5 standard error of point estimate, I think I did give you the standard error, the error formula. So 9.6 prediction of intervals. You please read that yourself, see if you understand it. I think it's not really not hard about prediction interval. Alright, so I will give you more examples on homework and then tell you how to introduce how to use the StatQuant to do the estimation problems. I need you to do at least 2 problems for each type of question manually, see if you understand it or can do it. Okay, thank you very much.